lost or unreadable for the robots. Why? Because they are being interrupted because of the congestion in the base station. So, in the movement format that we started this year, we would send 6 item data per packet at 60 Hz, which means 60 times per second. In this case, it gives a lot of congestion. Our base station cannot handle it, so 20% of the packets are lost. And how our path tracking system works? External computer calculates all of the trajectories that for each robot needed to move around. Then it will be sent all of those trajectories to the robot control module, so in order the robot moves out. Now, for fixing that issue, we tackle path tracking. We have a new system, so now we're sending 4 data items per packet in 10 Hz, which is 10 times per second. And as you can see, less packet means less load, and less load is higher chance of success of the packets to be sent to the robot. Now, in the new method, external computer, instead of having the full trajectories calculated, it will just calculate simplified 2D vectors, x and y. These x and y's will be sent to the robots, and all the calculation of trajectories will be on board of robots, since we have a very strong CPU on board. This will help us unload the base station command. So, what benefits? Number one is easier high-level planning. Now you can do way more planning because you have more options to send the sensors on. You can have less congestion, so it means that your packets have a higher chance of success to be sent right now. You have faster feedback loop. Why? Because it's simply not missing anything, so it's fastest as you can get. And last but not least, you can implement complex behaviors. How? Because you have an empty stack. Your stack is not full. Base station can handle way more commands, but you have empty. This gives us one benefit. Our AI team can now implement way more complex behaviors and send and receive way more data in order to run the robots better. Now I'm going to invite my AI engineer, Flim, my colleague, to explain to you more about that. Thank you very much.
Hello everyone, my name is Flim. I'm one of the AI engineers of this year. And together with my team, we've worked on pretty exciting stuff, and I'm here to tell you all about it. So this year we both focused on improving our current system, but also on pioneering something quite new in our competition. But before I tell you about that, let me first explain a bit about what we do with AI. Imagine you're a robot, the red robot, and you have the ball. But you see 3 robots standing kind of in front of the goal. Do you still shoot, or do you maybe move a bit to the side? That's kind of the issues we're dealing with. So, for our current system, our goalkeeper is now faster, so we can catch more balls. In addition to that, our AI spends less time on ineffective moves because we have revamped the decision-making logic, and we have also changed our AI a bit so it truly takes advantage of the new motors, which can move much, much faster, and also for longer speeds, longer durations. In addition to this, we also worked on edge cases, and these are essentially situations which are a bit rare, but they demand a very specific programming. For example, if the ball is really close to our 16 meters, now we just chip it away, we just get it out of there instead of, I don't know, trying to do some funny things with it. So, while these changes are pretty significant, we also felt like we were running against some kind of limit, because we were hard coding all of these behaviors, which also means our AI is only as smart as all of these situations we can come up with. So we started thinking, was there something else maybe that we could use for our AI? And we came up with reinforcement learning. Reinforcement learning is a type of machine learning that is known for learning quite complex behaviors. It has been applied to many games before, the Atari games, but also chess, StarCraft, and Go. These are all quite complex games, and this moment in 2016 was actually kind of huge because Google created an AI also based on reinforcement learning to beat a world champion at an extremely complicated game. So that was all quite cool. But first, let me tell you a bit about how reinforcement learning works. In a nutshell, it's an algorithm that works by trial and error. You have some robots, some agent, we call it, that's living in an environment, or like a simulated world. In the real world, it doesn't matter too much, but it gets information about where it exactly is, what's happening around them, and based on this information, the robot takes an action, maybe move forward or to the back, and if that action is a good action, we say, nice, and we reward it quite well. But if we say, if it's a bad action, we punish it, and we say, okay, if you're in this state, maybe next time try something else, because this is not working. Now, you might tell that this is a fundamentally different way of programming an AI. Instead of hard coding all of the behaviors, instead we now have an AI into some world, and we say to it, I want you to accomplish this, but we don't tell you how to do it. And that's exactly what we did. So our approach involves two major frameworks. One of this is called Mujoko MGX. It's a physics simulator developed by Google. And also BROX, which is a reinforcement learning framework. It kind of provides us with all the algorithms and pipelines, so we don't have to do everything, all of that ourselves. You might also ask yourself why we're all doing this in a simulation, and that is because in order for the reinforcement learning agent to learn anything meaningful, it needs millions of steps. I think in some examples I'll show you later, I think we trained it for 50 million steps, and it was kind of good. Yeah, but we also run about 1,000 simulations at the same time to kind of speed this up. Let me show you how it actually looked like. So you see a circle around the ball. It's a bit small, I hope you can see it, but this was our first attempt. And as you can see, it didn't really do anything. It was just kind of moving, it didn't go to the ball. So this means we had to try something else. Now, we can see that the robot's actually doing something, so that is good. But unfortunately, it's abusing the physics a bit, and it's kind of pushing the ball in instead of using our kicking mechanism, which is not what we want. So we need to change it a bit more. Now we can see that the robot actually kicks the ball, but it's not hard enough. The ball is not in the goal, but a lot of it is what we want. So let's tune it a tiny bit more and see what result we can get. So this looks quite good to me. This is yeah. So that's what exactly the behavior that we want to see. So in conclusion, we have demonstrated a basic proof of concept for a reinforcement learning agent in our simulation for our specific use case. And I also want to stress that this is just the beginning, because it's such a simple example, but in the end we want to make it much more complex, more agents, more difficult situations, but at least we hope to have set a foundation not only for our next year's team, but also for the other RoboTeam, teams around the world. Now, the technical part is over. I will give the floor back to Dave, who will tell you more.
All right, thank you, Flynn, and thank you all my other engineers. So, let's recap it a bit. What we actually learned this year. What we learned is that no matter what we build confidence, we build skills, we build robots, but also ownership, and especially we build a better and improved team. It's our individuals that hopefully through these improvements of the robots showcase their own improvements and how they have grown throughout the year and what they have managed to achieve. What is next? Well, Flim already announced it. It's a foundation in not only software, but also in our mechanical and hardware sense. It is a strong foundation that hopefully later teams can further work upon, and not only that, maybe other teams around the world can work upon. This also means that what is next is support from our side, because of course we, just like our alumni, would love to be on the sideline for the future teams and for anybody that implement our efforts, and we would love to see it financed. Now, this could not all be possible without my engineers, but also not all be possible without our sponsors and so many others. So I want to bring all my colleagues onto the stage together with you to say a proper thank you to everybody. So please, colleagues, come and join. So, we want to say thank you, and we want to first and foremost say thank you to all our sponsors. Our sponsors mean a lot to us, and they directly contribute to the end result of what you see here, the robot and this team. It's thanks to you guys that we are able to do this, that we can support doing this, that we can improve the way we improve, that we can not only build better robots, but once again, make better engineers. This is vital, this is awesome, and we cannot stress so much how thankful we are. It's also the crowd funds that help us a lot. These are people that support the team directly, and their support goes an immense way too. Of course, these crowdfunders, some of you might recognize the names, these are often family, friends, maybe even alumni. Last group I love to talk about, like it's the family, friends and alumni that are always there for us, supporting us through thick and thin, cheering us on, being always ready to pick up the phone when we need it, and it goes so far. So I truly mean it, that we as a RoboTeam want to say thank you. Showcase what we have done. My team and I will leave the stage. Well, this screen will hopefully rise, and there you will see our field behind it with our robot displaying all this. So if my team could please leave the stage. And please stand up and join us, talk to us, enjoy a drink. And if I'm correct, I have been told that this is a very slow process. Give us some time, enjoy the show. Look at all the plushies we have added to our year. Our new colleagues. But yeah, please be invited to talk. We love talking about what we did, and we have only presented so little. So, yeah. I hope to see you guys, and thank you so much for coming.